So welcome everybody. I'm so excited to being here and talking about the challenges of scaling Kubernetes custom resources. Could you please raise up your hands how many of you has some experience with custom resource definitions and operators? Oh, most of you. So you may also face with those challenges I would like to highlight today. uh, This is the boring slide, just to give some context about myself. My name is Rihát Kovacs. You can reach me on LinkedIn and GitHub as well. And I wrote my first business application in BASIC at 1993. I installed my first Linux Debian at 1997. I'm not that old, just started IT very young. I'm doing DevOps since 25. Earlier than we called it DevOps, we just called IT guys, cubes. I'm coding in Go for food since 2017, and I'm a Kubernetes addict since 2018. And the day since I recompiled Kubernetes is 1. And of course, I'm an open source devotee. And that's about me. I would like to start this presentation with a quote from Nelson Mandela. It always seems impossible until it's done. And it's very meaningful. And how many of you heard the sentence that this solution doesn't align well with the Kubernetes architecture? Most of you, I think. And if we look back to the history that stateful applications was not possible to run on Kubernetes and was not advised, or Windows workloads, or machine learning, or high-performance computing, or edge computing, those things were impossible in the past, but nowadays it's an average day task to run those kind of workloads. And the other thing I heard is implementing microservices with Kubernetes operators. This is impossible because the limitation and the architecture of Kubernetes, which I don't really believe in, but let's see why others do. In this diagram, you can see the Kubernetes architecture. I don't want to go very deep into this, into the details, but I split the architecture two parts. One is the brain, and the other one is the body. And as you see, the body contains multiple nodes. When we can run our workloads, we can have several of them. And it contains just a few Kubernetes components, and all of these components are working locally on this node. So we don't have to take care about the scaling of those kind of things. But if we jump to the brain part of the architecture, we can see we have an API server where the developers, operators are able to send the desired state of something. It should be usually core resources of Kubernetes like pods and services, etc. But also the custom resources and the definitions themselves are sent to the API server. So the API server saves everything, persists everything into the etcd, the backend storage, which is the truth of source in our case. It contains every desired state and the statuses. And also we have a controller manager, which across the API server actively watching the resources we create and update or delete. And it's called a reconciliation control loop. It fetches the desired state and tries to achieve that state. And we have a scheduler, but it's not important from this perspective. All right, so what are custom resources? Custom resources are extensions to the Kubernetes API to create, read, update, and delete user-defined services. And what are operators? Operators are user-defined controllers to react on these custom resources we created. But if we check this slide of my presentation, we can realize that custom resources and operators are some kind of mixture of brain and body functionalities. So if we would like to scale it and create thousands and hundreds or millions of resources, we have to take care on both sides of the Kubernetes architecture. Let's jump to the easy part of, as I earlier mentioned, that the body can contain multiple nodes where we can spin up the operators. But the cache inside the operator is the heart of everything, because our operator gets every event when we create or modify a resource. And just a simply overview of how it's working. So the operator registers itself to the Kubernetes API server to watch certain resources. Then Kubernetes API server sends every update or create event. Inside the cache, there is a queue where it can put the resources one by one. And it puts to the local cache into the memory. And also there is a cycle when it's regularly refreshes, resynchronizing the cache itself, and based on the last known version of the resources. So as you see, if you have more than 10 or 100 custom resources, all of them would sit in the memory of the operator. If you are thinking in scale of operators, then you have to forget the leader-elected operators, because by default, every operator is leader-elected, so only one instance is running, and that instance is managing or dealing every resource changes. So you have to design some kind of distribution of the operators, which is not trivial, and I don't know, please fix me, but I don't know any existing tool to make this seamless. You have to take care on the reconciliation concurrency, how many of resources you can change or modify in the same time. You have to configure the rate limits, bursts, and timeouts of your clients. And if you have lots of resources, you have to count with the longer startups of the operators. For example, fetching 100,000 resources from Kubernetes should take 5 minutes or 10 minutes. So this is a big challenge. And I strongly advise you to retry fail actions, because by default, if you send an error from a reconciliation loop, it puts back to the queue. And sometimes later, when it reaches that point, it will consume that event again. But I strongly suggest to make some retry mechanism in your operator to avoid this requeuing process. And also you have to find the best scheduling for the cache synchronization period, because it's not fancy to resynchronize the cache every 5 minutes if fetching the data is 10 minutes, of course. And another nice point is you can filter what you watch by the labels. And that's the point. You have to implement some distributed consuming process based on the object labels. All right. So jump to the heavy part of the architecture is the brain. Then the components are playing some role in the custom resource definition management. One is the API server, which is handling the CRUD operations. And the API server is leader elected, so there is one instance actively running. All the other instances are just cold ones and waiting for activation.
Okay.
The controller manager is the other component. It mostly does the garbage collection of the resources. It is also leader elected, so you have only one instance. And the third component is etcd, the data store itself. And what a surprise, it is a leader elected architecture, so you have only one instance which is actively waiting for the database requests. So I'm almost running out of time, but let's see. So the difficulties in scaling for the API server, that you only can scale it vertically, big business, big machine, that I can suggest. There are only a few options for the performance optimization, and the main ones are you can disable the watch cache or set the maximum requests in flight in the API server. You would need a huge network bandwidth because of watchers are everywhere, so you have lots of connections connecting to the API server. Regarding to the CPU and the memory, is infinite if it's possible. And regarding to the watch cache, that you can set the size of the watch cache, but it only affects the built-in resources, so custom resources don't have any benefit of the watch cache size. And so that means that every custom resource sits in the memory of the API server. The other big challenge here is the client-side filtering of API server. So when you set a label or a field selector, then the API server fetches every data from etcd and does the filtering in place in memory and sends only the filtered result back to the client. But it's very memory and CPU and network high load. Sorry. And then one point I would like to mention, it's very funny, that if you have multiple versions of the custom resource, then you have specified the storage version of the custom resource. So that means the API server fetches everything and then converts it from storage version to the latest version and then apply the filtering. So it's lots of CPU power again. And a big challenge would be the discovery endpoints, because every resource would have, so Kubernetes has a dynamic API where you can fetch the supported features and resources and whatever so on. But every new custom resource definition adds to the time of doing the discovery requests. Jump to the controller manager. It's vertically scaling, big business, big machine, and the memory is, and the CPU is infinite if possible, of course. And what I would like to highlight is the controller manager doing the garbage collection. So it has a metadata cache for every object. It means every object you created fetches them in the startup, caches every object, and receives every message regarding to every object. It's not a fun part, but that's how it works. Quickly jump to the etcd, the data source side. It's scaling vertically again. Because of the consistency model of the Kubernetes, that sharding the data is not possible. So every single record is stored in one single instance, and then it's replicated to the other ones. The storage throughput is very critical because etcd has a memory mapped storage, and it stores lots of things in the memory. Regarding to the CPU and memory, infinite as possible, of course, mostly because it has the in-memory index I earlier mentioned, and etcd heavily depends on the page cache of the operating system. The network bandwidth is the same as the API server, because every watcher lands into the etcd server. And the recommended maximum size of an etcd database is 8 gigabytes, but who wants to push it to the limits? So it should be less in normal cases. So it's time to define big. What does it mean, big in Kubernetes? If we check the documentation and the limitations we should face is no more than 1,500,000 total pods, no more than 300,000 containers, no more than 5,000 nodes, and no more than 110 pods per node. From this list, the orange ones are related to the brain part. So those are the most trickiest one. So if you check the numbers, it's not too much. I mean, maybe you would have a few more config maps or secrets, but the total number is lower than 1 million, of course. So running that big scale Kubernetes is very hard because it's not designed by default. So it's time. I would like to jump to the scaling of custom resources. I can define 2 dimensions of the scaling. One is the horizontal scaling, when we add more and more custom resource definitions. So adding custom resource definitions adds complexity to the API server, which should degrade the performance of the API server. The more custom resource definitions means more and more controllers, and this should increase the management overhead of the cluster itself. And as I mentioned earlier, that the API discovery can quickly become a bottleneck. The other dimension of the scaling is increasing the number of custom resources. More custom resources we need more storage, network, and CPU. Adding more custom resources leads to adding more operators, but more controller replicas amplifies scheduling and monitoring those pods. And also the event processing should be, the number of messages should be very high. And the tons of requests will delay normal cluster operations. So if we create 1,000 custom resource at a time, and the API server is handling it hardly, then it can take other cluster-related tasks. So if we have a cluster failure, we can't realize it until a while. Just a few words about the horizontal scaling, that the problems tend to start happening once you are over than 500 custom resource definitions. You have to take care on the client-side rate limits and, importantly, in the burst to avoid overloading the Kubernetes API server. Some clients, like kubectl, is not designed to have more than 100 of custom resource definitions. So you have to be aware of what kind of clients you use. It's not a big advice, but thankfully for the crossplane team that they changed Kubernetes at 1.26, and they increased performance of handling custom resources and definitions. And you have to count with longer startups and memory and CPU peaks during the startup in both Kubernetes API server and controller manager. When we are speaking about the vertical scaling, you have to count with longer startups as well, and take care on the client's timeouts, because some operator or some clients are not designed for 10 or 20 minutes of response time. You have to disable watch cache, which the reason of watch cache is speeding up database operations by everything is sitting in the memory. So Kubernetes don't have to reconstruct every record in the memory. And what you can do is replacing etcdiff to Kine. I don't know how many of you is familiar with Kine, but it's a middleware between the database and Kubernetes and translates etcd requests to SQL or any other database requests. I have found a watch cache bug in Kine, so if you disable watch cache, there should be some issue during the creation of events, but I opened the ticket. Hopefully, they will fix it soon. The other thing you can do is offload your Kubernetes API server. There are alternatives. The one I am most familiar with is the KCP, which is a horizontal scalable Kubernetes API server-like solution. Or you can run a proxy in front of Kubernetes API server to help them on a high load. Another quote, this time from me. Watch cache is your enemy. And in this chart, you can see the free memory of a computer I created and tested. And I created 20,000 of custom resources. And as you see, the free memory goes low and low. And can anybody tell what's happened in the middle? It was a crash, yes, because the operating system just out of memory killed the API server, which is not fun. And when it restarted a few minutes later, it started to load every data from the database. So the same happened. I found myself in a loop of out-of-memory crashing. And unfortunately, the multiple replicas don't solve this problem because the other will pick up the same data set. And I earlier spoke about the reason of the watch cache is to speed up the database operations. I created a small benchmark to fetch 50,797 resources from the database. And without watch cache, it was 50 minutes. Yes? 50 seconds, 50 seconds. But with watch cache, it was more than 1 minute and a half. So, does it speeding up things in high scale? No. Watch cache is your enemy in high scale. There is another chart from creating 60,000 records across 3,600 threads. This time I swapped to MySQL via the Kine plugin I earlier mentioned, and it took more than 1 minute. The average response time was 620 microseconds, and the maximum response time was more than 3,500. But the important thing I would like to say here is I was not able to scientifically prove this, but in my experience, if there is lots of create events, then somehow the API server or database or some cache or something in the architecture prioritize those operations. So if I send an update event in the middle, it's just delayed until lots of create events happen. So that means if you pushing your API server or your entire Kubernetes architecture to its limit, you possibly find yourself in a situation where it can't respond to normal cluster operations, which is not so fun. Raise your hand if you think it's fun. So just a quick recap of my presentation that Kubernetes API Server, Controller Manager, and etcd are single point of failures. They don't scale so well. Millions of custom resource needed infinite resources. Some clients does not tolerate huge data sets or large timeouts. it is pretty easy to kill a Kubernetes API server with a single list call. So it stops the word. And a middle tier performance with this architecture requires lots of care and understanding what's happening, needs a complex architecture, and it is, I can say, impossible without custom components and business logic, right? So I don't believe in it, but well, we are not there. But it always seems impossible until it's done. So in the second presentation in the keynote, I open sourced the storage side filtering, custom versions of Kubernetes and Kine for storage level filtering. It's just a proof of concept, of course, and my plan is to highlight it to the community and maybe others also see the possibilities in this change. And we are working in a middleware, a Kine-based middleware, to replace etcd to a multi-database, vendor-agnostic database topology without changing anything in your workflows. This is not a marketing pitch, but if you are interested in how to scale your database to 10 times or 20 times, please feel free to discuss with me after the presentation.